Great. So thank you so much for joining us today at the ArchiPro webinar in conjunction with Waterware. My name is Holly and I am campaign manager here at ArchiPro. Just a little bit of housekeeping before we get started. If everyone can just make sure that their microphones are on mute, and any questions that you have throughout today's session, just pop them into the Q&A box at the end, and we will answer them at the interactive Q&A section. In today's webinar, we will be learning about engineering modelling tool Net Zero, led by Waterware technical engineer Darren. We will then be joined by ArchiPro's managing editor Joe, who will lead the interactive Q&A session. So as mentioned, any questions that you have during today's session, please pop them into the box below. So without taking up too much more of your time, I will now pass along to Darren. Thank you, Darren.
Thanks, Holly. I'm Darren from Waterware. I run the engineering team. We're specialists in high-capacity hot water systems, amongst other things which we do. We've got a very long history in producing hot water for multi-tenant buildings. Traditionally, we've always used gas and diesel technology, but as things have changed over time and the move to renewables, we're starting to deliver these new solutions. So one thing I just want to cover off to get started is to let's make sure this moves. Okay. Is to explain the difference between two types of method of producing domestic hot water. So the most traditional is seen on the right, which is a decentralized hot water, where we have one electric hot water cylinder per apartment. This is the most traditional style of doing hot water. It's the most similar to a typical house, and we see it quite commonly in smaller apartment buildings. Typically, as the building goes above about 20 apartments, systems tend to move towards centralized, and centralized is seen on the left. So centralized hot water is where we produce all of the hot water in a centralized plant room, and then we distribute it through the building to then feed each bathroom within the building. So some of the key differences, the reason why you would move from a distributed hot water system, a decentralized hot water system to a centralized, is the main driver, especially when we're using gas appliances, is capital efficiency. Typically what you tend to find is once you go above 20 apartments, it's, from a capital point of view, cheaper to produce your hot water centralized and then circulate it through the building than it is to produce it in each apartment. In terms of space requirements, typically for a building, let's say you've got 100 apartments, the plant room required to hold the equipment to produce that hot water is typically maybe 3 by 4 meters. So you might be looking at 12 square meters. If you were going to do that decentralized, then you need to have a hot water cylinder cupboard in every apartment. As the cost per square meter of apartments go up, then this number starts to add up. So if you don't have to set aside a hot water cylinder in every apartment, then you get to liberate that space for something else. One of the disadvantages of centralized and one of the strengths of decentralized is redundancy. So what that means is if you have a problem with your plant, if you're in a decentralized hot water where you're producing the hot water in the apartment, then you only take out one apartment. So the rest of the building will run quite happily, and then you'll have just one apartment which doesn't have hot water. With a centralized hot water system, if it goes down, you lose hot water to everywhere in the building. So some of the ways which we mitigate that risk is by having redundancy built into the plant. So typically we'll have multiple heat sources and multiple cylinders so that if you do have a problem, it doesn't take out the entire plant. You can always produce hot water to some level, and at least the building can limp along until it gets serviced. One of the things that commonly gets asked is heat loss. So with a centralized system, you have a return pipe which runs through the building. So you have a hot pipe which links all of the apartments together, and then you have a return pipe which brings the water back. And the reason for that is if you don't have a ring main or a return-based system, it takes a very long time for the hot water to go from the plant all the way up through the building to the last apartment. And so to prevent that wait time, you circulate water within the building all the time. So when you turn on the tap, it's only coming from the main rather than coming all the way from the plant room. So one of the things which people normally question is what's the heat loss out of that pipe relative to a decentralized system, which doesn't have a ring main. Typically what we tend to find is when you've got centralized plant, the amount of water that you're storing in the cylinders, typically you might have 2, 3, 4, 5 big cylinders, versus if you're in an apartment with 100 rooms, you'd have 100 hot water cylinders. What you tend to find is the heat loss out of those 5 big cylinders in ring main is lower than what you get out of 100 electric hot water cylinders. So the water cylinders themselves aren't particularly well insulated, and they become more well insulated as they get bigger, which is a little bit counterintuitive. But in terms of heat loss per litre of water stored, you lose less energy as the size of the cylinders go up. So that's just something to keep in mind when we're thinking about the overall efficiency of the system and some of the reasons why you wouldn't go decentralized versus centralized. Okay, so another key technology which we use in this system is air-to-water heat pump. And I'll just contrast that to an electric element system. So if you're going to go decentralized and you're going to have hot water cylinders with electric elements, then there's certain limitations which go along with that, or there's things with that technology which, when you compare it to an air-to-water heat pump, it becomes obvious why you would use an air-to-water heat pump to produce hot water. So one of the key points to contrast an air-to-water heat pump to an electric element, with an electric element, if you pass it 1 kilowatt worth of electricity, you get 1 kilowatt worth of heat back. And so in effect, it's 100% efficient, or normally they're like 99% efficient. So in terms of when you're comparing that to a gas or a diesel boiler, then that looks very, very good, because a gas or diesel boiler is typically, if it's condensing boiler, maybe 90% efficient. So when you compare that to electric element and it's 1 kilowatt in of energy and 1 kilowatt of heat out, that looks very good. But when you compare that to an air-to-water heat pump, you start to understand why this technology is really diffusing through the market. So if you pass 1 kilowatt worth of electricity to a heat pump, it doesn't transfer that directly to heat. What it does is it uses that energy to run a process. And the process is it takes air from around the appliance and it passes through this finned coil, and it extracts the energy from the air. And the real magic of that system is it can do it at a ratio, and the ratio is normally stated in terms of COP, coefficient of performance, and it's quite magical the way it works. So if I give a high temperature air-to-water heat pump 1 kilowatt worth of electricity, it can harvest heat from the air at a rate of 3 to 1. So 1 kilowatt in, 3 kilowatts out. So immediately you can see, okay, so if you were going to state that in terms of efficiency, the heat pump itself is 300% efficient, which obviously doesn't make sense to me. How can you get more energy out than you put in? And it's because we're not directly converting the electricity to heat. We're using it to run this process. The heat actually comes from the outside air. And these appliances are very robust. So they will operate right down to about -15. So the COP of the appliance falls when you get into that very, very low temperature, but it still operates all the way down to those sort of levels. So typically, if you've got an outdoor air temperature of around 7 degrees, is normally the benchmark. If it's producing hot water at 65 degrees, then the COP is 3.1 to 1. So 1 kilowatt in, 3.1 kilowatts of hot water out. In terms of capital cost, these units are quite expensive. But when you compare the cost of producing hot water in a decentralized model, so with multiple electric hot water cylinders versus a centralized model, the centralized model is much more capital efficient. So if we were going to do a gas centralized system, typically the cost parity occurs at about 20 apartments. So 20 electric hot water cylinders costs about the same as a centralized gas plant to produce that much hot water. Then as you add apartments, then it gets proportionally cheaper and cheaper and cheaper. With an air-to-water heat pump system, typically the break-even is a little bit more expensive. The heat pumps are more expensive per kilowatt than a gas boiler system is. So the break-even for an apartment is about 40 apartments. So 40 electric hot water cylinders costs about the same capital cost as what a centralized air-to-water heat pump system costs. So one of the reasons why this technology is being adopted rapidly now where it hasn't been in the past is there's recently been a change in the type of refrigerant which is used in these appliances. So it used to be that the older appliances used a gas called R410A, or more recently they've moved to a new gas called R32. As part of the Paris Climate Accord, there was a new standard which got brought in related to a metric which they call GWP, Global Warming Potential. And it's a score which they give the gas to the amount of damage it does to the environment if you let a quantity of it out. Now, the gold standard in terms of refrigerants is CO2, that has a score of 1, and then all the gases stack up behind that. So to give you an example, the GWP of R410A, which is the old legacy gas, it's about 2,500 units. The more recent R32, which is quite diffused in the market now, has a score of about 650. The refrigerant which we're using in our appliance is called R290. That has a GWP of 3. So it's pretty much inert. It's very close to what CO2 is. The advantage of this new refrigerant is it now changes the operating range of the appliance. So the old R410A and the old R32 appliances, they used to top out in producing hot water at about 60 degrees, which isn't quite hot enough to reliably sterilize the tank for Legionnaires. So that's what typically held back using air-to-water heat pumps in these commercial applications was the primary temperature they could produce wasn't quite hot enough for the job. And so what tended to happen is they'd have an air-to-water heat pump backed up by electric elements. Now, whenever you back up by electric element, the element runs at a COP of 1:1, which brings down the overall operating efficiency and COP of the system. Now, with the new R290 appliances, they go up to 75 degrees. And so now we have enough headroom to produce that hot water without using any electric boosting. And so it means the overall COP of the system is much higher, and the system itself is quite a bit less complicated in terms of control and implementation. Okay, so these are the primary technologies which we're looking at. Here we go. Okay, so what we're doing with this net zero project, this net zero solution, is we're taking this high temperature air to water heat pump and we're offsetting it with a solar PV array. So if we put a solar PV array on the roof, every kilowatt of electricity which we produce with that system, we're levering at a rate of 3:1. So we supply 1 kilowatt of electricity to the heat pump, it gives us back 3 kilowatts worth of hot water. Now what that does is it really drives quite a strong capital efficiency. So if you're going to put solar on your roof and you're going to use it to run your lights and your fridges and electric hot water cylinders, for instance, every kilowatt of electricity you produce, you only get 1 kilowatt worth of hot water back. But if I combine that with a high temperature heat pump, now every kilowatt I produce of solar PV, I'm turning into 3 kilowatts worth of hot water. So that means when you look at the cost relative to what you get back, it radically reduces the payback time of the system. So what we try and do is we create a model for how the system needs to operate, how much water we need to produce to shower everybody in the building. Once we have that information, we then work out how much water I need to supply, how much water I need to store, what rate I need to recover it using my high temperature heat pump, and then that drives the size of the solar PV array. And once you get these things in the right proportion, the storage versus the recovery versus the solar array, the capital efficiency of the system comes right down. So typically what we tend to find is we're at cost parity. For a system, when we size, what we try and do is we try and get the proportion of the system right so that the total amount of energy which I require to produce my hot water over the year is the same amount of energy which the solar PV system produces over the year. So in effect, you're carbon neutral and you're close to zero running costs. So it's a very, very attractive solution. It's something which is quite unique to think about it in this way. And because you're getting that proportion right with storage, recovery, and solar PV, the capital efficiency is really good. So once you go over about 50 units, we're at cost parity at what a decentralized hot water cylinder with electric element solution would be. So if we weren't going to do the solar PV offset, then we're at cost parity at about 40 apartments. But including the solar PV array, we're about 50 apartments. We're a little bit glitchy here. Where are we? Okay, so sorry about that. My computer's going to sleep. Too much talking. So the way the engineering tool works is we develop a power requirement model. And so what that does is we take the total occupancy of the building and we allocate a certain number of litres per person. And there's quite a well-established guide which we use for doing this. So as an example, we calculate how much water is required per person at 60 degrees C. And the scale normally runs from, if you're in like a backpackers, very entry level sort of building, you would allocate 25 litres per person. And if it's 5-star residential, then normally you would allocate 50 litres per person. So there's a scale in between depending on the quality of the building, the sort of the level which you're trying to achieve. So once we get the occupancy and we get the total number of litres per person, we design the system so that we can shower everybody in the building over what we call the peak period. So when we're talking about multi-unit residential, typically you have 2 peak periods a day. You'll have a peak period which runs from 7 a.m. to 9 a.m. and then another one early evening, maybe 6 p.m. to 8 p.m., about half the size typically. So we will size the system that we can shower everybody in the building during that first peak period. So once we calculate how much water that is, we can then generate this power requirement model. So into the model, we take the total capacity, how much water we need. We take the groundwater temperature, so how cold the water entering is, and that gives us our total amount of energy required because we're producing the water at 60 degrees C to meet our requirement. And we also drive into the model, we use average air temperature. And the reason why average air temperature is required is the COP of the heat pump, the efficiency of the heat pump, is related to the temperature of the air which it's using to harvest the energy from. So if you're in an environment which is really cold, the COP is lower. If you're in an environment where it's mild and it's warm, the COP is higher. So into this power requirement model, we take groundwater temperature, the air temperature, and the total capacity, total production requirement, and that produces this model. And you can see that the total amount of energy required to drive the heat pump is lower in the summer and higher in the winter. And so it creates this kind of bell curve. And so we take that information, that's the input to our model, is this power requirement. Then we use that to drive the size of the solar system. Okay, so the power production model. This is how much energy my solar system will produce over the year. And you can see that the curve is inverted. And that is because you have much more solar gain in the summer, solar hours in the summer than you do in the winter. So it's the opposite of what our power production model, our power requirement model is. So to produce this model, what we take is total number of panels, which we put on the roof, and the mean daily global radiation. So very helpfully, NIWA publishes this data for us. They give us groundwater temperature, they give us average air temperature, and they give us the solar radiation by region. So we can put in which region the system is, and then it creates this model, which gives us these curves. So then what we do is we take those two curves and we put them together. To create this energy balance. So what we're trying to do is we're trying to get the size of the solar system exactly matched to the requirement that we need to produce the hot water running through our heat pump. So if we get that, once we get that balance right, what that means is the system itself is operating in a carbon neutral way. The total amount of energy we're producing with our solar system is the same amount of energy which our heat pump requires to produce the hot water for the building. So when you get those things matched so that over the annual period, your energy balance, the capital efficiency of the system is very, very good. That's when we're kind of where we're getting to cost parity with an electric element system at about 50 apartments. Okay, so the process which we use to develop a solution, we start with the planning. So that's basically what's the occupancy of the building, what's the size of the roof area, and we take those that information and then we create the model using the NIWA climate data for the area to then optimize the solution. So we work out how much hot water are we required to store, what rate do we need to recover it to meet the next peak period, and then what size solar system is required to offset that annually over the year. So at the front side, we have this engineering tool which drives the specification of the system. It also can allow us to do some QSing, so we can quantity survey a realistic installed cost which the client would pay. And then on the back side, typically that will be peer reviewed by an engineering company. Typically what happens is we'll produce a solution for the job that will go to an engineering company who will then QS it to make sure that they, to peer review it, to make sure that they agree that we've got the sizing right and that our numbers look correct. Then that will go out to tender. There'll be a building company who will win the job. They'll employ a plumber to install the system. And we have this wraparound support service. So during the installation of the system, we have on-site support where they'll take a couple of visits during the construction process to make sure the installation is heading in the right direction. And then during commissioning, we'll be on site to commission the system. So we're trying to create this wraparound service where we've got the engineering and specification at the front with QSing, and then at the backside, then we're doing actual installation support. Because these technologies are quite new, the market really needs a high level of support to deliver these types of solutions in sort of a low resistance way. And so that's how we're thinking about the services we provide to the market is basically this wraparound service to try and reduce the number of problems and deliver a solution in a low resistance way. Okay, so hydraulically, this is the way the system typically works. So this example, we have two air to water heat pumps. So the air to water heat pumps are on the left-hand side. They connect onto this centralized buffer, which just combines the two heat pumps together. And then we transfer the energy from that indirect system into the two 1,000 litre tanks, which is on the right. So I spoke before about one of the issues or one of the weak points of centralized systems is having redundancy. All of the systems we supply will have at least two appliances on the recovery side and at least two cylinders on the storage side, but it runs in a modular way. So if we need 4,000 litres of storage, we'll have four 1,000 litre tanks. If we need 48 kilowatts of recovery, we'll have three heat pumps in cascade. The control of the system has some quite good smarts built in. And one of the functionalities that it's got is it's got cascade management of the appliances. So it evens the runtime over the appliances. So if one appliance does more work than the other one, it reorders the array once a week so that you get even runtime across the appliances. And it also has some quite smart moving set point technology. So what that allows us to do is we can set a minimum acceptable set point in the storages at 55 degrees. And then the system can sense that if the solar system is in production, so if the solar system is producing electricity, we can dynamically change the request in the hot water cylinder up to 70 degrees. So what that allows us to do is when the solar system is in production, rather than have that backfeed the building and be used to run lights and fridges and everything else on standby, we can preferentially use that energy, run it through the heat pump, because every kilowatt of electricity you run through the heat pump, you yield 3 kilowatts of hot water. So that is your preference. Whenever your solar system is in production, if at all possible, you want to be running your hot water system in recovery mode. So because we've got this moving set point technology, it means that if the system drops below 55 degrees, doesn't matter whether the sun's shining or not shining, the system will recover the hot water. It takes energy from the building and it recovers the hot water system. If the system senses that the solar system is in production and we're actually producing electricity, it will then dynamically change the request in the cylinders up to 70 degrees to allow us to build energy and build hot water into the storage system. And it's like an energy bank. The advantage of using this sort of philosophy with a solar system is it's much, much cheaper to store hot water than it is to store energy in lithium-ion batteries. And lithium-ion batteries aren't very environmentally friendly, and they have they're quite expensive. So to do it in terms of storing it in hot water is much more capital efficient. So the solar system and the heat pump system isn't directly connected together, like physically connected together. It's connected together logically. And the logic is the system can see when the solar system's in production. If the temperature of the water in the tank is less than 70 degrees, the system will then kick into gear and start building energy into the storage cylinders. Now, if that dynamic boost, so we call that solar boost, if that solar boost functionality doesn't happen during the day, the system can automatically then do a Legionnaire's purge in the tanks. So if the system hasn't gone above 60 degrees during a 24-hour period, the system will automatically boost the hot water to sterilize the tanks as part of the normal operation of the system. So you've got 3 basic set points which the system runs on: minimum acceptable 55, dynamic boost 70, and then Legionnaire sterilization at 60 or 65, depending on how you set it up. So all of that functionality is built into the controller and just happens automatically. You don't have to schedule it. It's built in. Okay, so the key component of the system, or one of the key components, is the heat source. So again, this is featuring R290 refrigerant, one of these new generation natural refrigerants. Again, the key benefits of this refrigerant is it's got a very low GWP, global warming potential, of 3. So it's basically inert. It's very similar to CO2, which is the other gas which has been used. But the key advantage for us in this application is high temperature output. It will go up to 75 degrees. So that allows us to reliably sterilize the tank. It allows us to do this dynamic boosting when the solar system is in production. So the controller, this does the cascade functionality of our heat pumps. It allows us to have even life across the heat pumps. The heat pumps themselves have got a very wide operating range. So they will modulate from 30% to 100%. And then if you have them in cascade, it will run in a stepped way. So if you're just recovering heat loss out of the loop, or one person has a shower in a large building, then only one heat pump will come on, and it will only run at 30% capacity. And then it'll stage as more load comes on, it'll bring on the following appliances and modulate them all up to 100%. And then once a week, it'll reorder the array. So the one that's done the most work now becomes the last, and the one that's done the least now becomes the first. So that all happens automatically. We can cascade up to 8 appliances with one controller. So it gives you an idea of the scale and scope of the system. You can build quite a big hot water system. A 100-room apartment is not a problem in terms of capacity. The other advantage we have with this controller, again, is this moving set point technology, where I can set a minimum acceptable set point at 55, dynamic boost at 70, and then Legionnaires at 60. All automatic, all run from the time clock. The system you can also connect, so you can do offsite, not maintenance, but offsite monitoring of the system. It'll send you automatic alerts if one of the heat pumps has an error. So that sort of functionality is all built in as well. Okay, so hydraulically, the water we keep in the heat pump is indirect. So it's like a mechanical based system where we have water that's in the heat pump and in the buffer tank is kept separate from the water that's inside the hot water cylinders. And we do that with a high capacity plate heat exchanger. So the water that's in the tanks never actually passes through the heat pump. It's kept separate. And then the storage cylinders, we have two platforms, either 500 litre or 1,000 litres. And again, we run them in an array. So if we need 3,000 litres of storage, we'd have three 1,000 litre tanks. Again, we'd always run a minimum of 2 cylinders. So we have some sort of redundancy built in, but typically you find you have more than 2. We used to use bigger tanks than 1,000. We used to use 2,000 litre tanks. So if you needed 2,000 litres of water, you could do it in an individual cylinder. But what we've learned over the years is that when the cylinders need replacing, if you go bigger than 1,000 litres, you can't get them out of the plant room very easily. So we tend to use these modular solutions more and more now, where we'd rather use multiple 1,000 litre tanks than fewer larger tanks than that. Just getting them in and out of doorways and in and out of plant rooms is pretty much impossible with the bigger diameter tanks. Okay, so when you're producing the water centrally, you have to distribute the water through the building. And typically, if it's multi-unit residential, you'll circulate that water at 55 degrees. So there's a requirement for Legionnaires where you have to store your water greater than 60 degrees. And so the controller will do that daily if it doesn't happen with the dynamic boost. But you don't want to distribute that hotter 70-degree water directly through the building. So this valve blends that water down, so you're delivering 55 degrees to each apartment. The advantage which we've got with this Legio mix style valve is it's got data logging built in. So it keeps a log for 30 days. Every hour, it'll tell you what temperature left the plant room and what temperature came back. So if there's any troubleshooting required, you can tell whether the problem's happening in the plant room or inside the building. And then, of course, if you're charging for the hot water, then you need to have a water metering system. So one of the advantages we've got as a company is we've got a very, very broad product offering. So we can go right from the production side with the heat pumps, with the storage cylinders, with the blending valve, which circulates water through the building, but we also do the water metering system. And there's two types. You can have either a wired, which is Modbus, which connects into a building management system, or we can do a standalone wireless system where it talks to a GPRS modem and will send you an email once a month to do billing. So there's hot and cold water meters, so you can charge for all of the water. If you combine them together, you can also charge for wastewater. Okay, so here's an example, a worked example of the output which we get from the engineering tool, just to give you an idea of the scope of the system. So this particular building was 57 apartments and the maximum occupancy was 119 people. So we use that to drive the engineering tool for the total capacity. And this is an example of what the engineering tool will put out. So we have the production requirement at 4,700 litres. And we're storing 2,000 litres of water with 64 kilowatts of recovery. And it tells you what this recovery period is. So after serving the first peak period, it takes 3.9 hours to recover the system. So one of the things which we're trying to do when we're designing the system is getting the proportion right between the amount of storage which we have and the rate at which we can recover it. When we do gas-based systems, because gas is very cheap in terms of cost per kilowatt, in terms of appliance cost. It makes sense to have a smaller amount of storage and a higher amount of recovery. So you can store a small amount of water and then you might recover it over half an hour or at maximum an hour, normally with a gas-based system. We use a slightly different philosophy when we come to air to water heat pump systems for two reasons, especially when we're offsetting with solar PV. Two reasons. So the first reason is the air to water heat pumps themselves are very expensive on a cost per kilowatt basis compared to a gas appliance. So it makes sense to have more storage and less recovery because cylinders proportionally are very cheap relative to heat pumps, which are quite expensive. The other thing which we want to do is we want to make sure that we're maximizing the solar window. So when your solar PV system is in maximum production, you're preferentially running that energy through the heat pump and storing it as hot water. So the peak solar window during the day is typically from 10 a.m. to 2 p.m. So what we're trying to do is we're trying to arrange the system so that we recover the hot water from the peak load from the first peak period over a period of about 4 hours. And so this recovery period lets us know how we're doing in terms of getting that sizing right of storage relative to recovery. Now, this next section here tells us how the overboost performs. So this is taking the system from the minimum 55-degree set point up to the maximum of 70 degrees. So this is this dynamic boosting behavior where we're trying to make sure that if the sun is shining, we've got enough headroom to store that as thermal energy rather than just use it as electricity. So that gives you the sort of shape of how much energy you store and how much it's costing you and how long it takes. So in the system where we've got 2,000 litres of storage, the energy required to take that 2,000 litres of water from 55 degrees up to 70 degrees is 35 kilowatt hours. But that 35 kilowatt hours is only costing us 11 kilowatts, and that's because of the COP of the appliance. So 11 kilowatts of electricity, I'm turning into 35 kilowatt hours of hot water. And that overboost takes about half an hour. So that gives me an idea of how the system is performing relative to my peak period, which might finish at 9 a.m. and then my next peak period, which might start at 6 p.m. I've got this window in the middle of the day. So I want to be able to recover my whole system and boost it up to 70 degrees over the period of about 4 to 5 hours maximum. And so this output allows us to get a handle on just how we're going in terms of getting that proportion right of storage versus recovery power from our heat pumps. So the next section down talks about getting a shape around the solar requirements for the system. So the inverter I need to drive those 64 kilowatts of heat pump is a 20 kilowatt inverter. The solar panels, which are required to produce the same amount of energy which my heat pumps consume annually, making sure that we take account for, we've got the bell-shaped curve for the production requirement, and then the inverted curve for the production from the solar system. So for this particular system, with the to produce that 4,700 litres of water, we need 61 solar panels, which takes up about 102 square metres of roof area. So very quickly, you can have a sense check about whether this actually fits in your building. Do you have 102 square metres of roof area on your roof to house the solar system? So we use these type of metrics along with what the QS of the actual capital cost of the system is to then sense check about, okay, is the system practical in terms of space requirement, in terms of capital, in terms of running cost and carbon, which we'll get to in a second. So down towards the bottom of this report, we have some cost analysis of running costs. So, and the comparisons we do is, the first one is, if I was going to produce that hot water with a distributed system where I was going to use electric hot water cylinders with electric elements, the running cost per year of the system is about 27,000 per year. If I was going to do the same system but with a centralized gas, it's about 7,500. If I was going to do centralized heat pump without PV offset, it's about 8,700. And then with the offset, it's a slight refund. So my solar system slightly produces more energy than what my heat pump consumes. So you won't actually get a $210 credit, but you'll use that energy soaked up in the building. So the opportunity cost of not having to buy that power is $210 per year. Then we can do the same in terms of carbon. So what we tend to find is in the institutional and government work, they're very, very focused on carbon metrics. So as part of the tool, what we can do is do carbon comparisons. So if we were going to produce that hot water using electric elements and hot water cylinders, it's 11,500 kilos of carbon per year. With natural gas, it's 23,000. With the heat pump system, it's 3,700. And then with net zero, it's a slight carbon. You're in the positive for carbon. So you can very quickly see, like if carbon is your main metric, which you're very focused on, if you could do if you had the choice between doing a gas centralized system and a heat pump system, you can very quickly quantify the difference between the capital costs and what your carbon performances are. And so this particular system, you're reducing your carbon footprint by 23,000 kilos per year, which is really significant. So for the right audience, these type of metrics allow the client to make these informed decisions about, all right, this is what my capital investment's going to be. This is what my estimated running cost is. This is what my estimated carbon footprint is. So it's a very good tool to allow a client to make informed decisions about which way they want to produce their hot water. Okay, so this is just an example of all of the primary components which are in the system. We can use this tool to drive a high-level QS, so the client can have an estimated installation cost of what the system is, and then we can compare it to different types of solutions. So this is just the overview of the power requirement model, the power production model, and then the energy balance. So you can see kind of how that stacks up. You can see the annualized COP of the systems, 3.1 to 1. This particular system was in Auckland, so it uses that NIWA climate data to create as accurate a model we can. And again, this is showering everybody in the building once a day. So it gives you just a basic idea of the expected performance of the system. So we have our running cost comparisons, which is just from the table above. And then we have an example layout of how the system works. So this particular system is 64 kilowatts of recovery. So we've got 4 units in Cascade and 2,000 litres of storage. So because we know how many appliances there are, and we know the size of the appliance, which is as detailed here, then pretty quickly you can then set aside an allocation for how much space is actually required outside the plant room for the appliances, inside their plant room for the storage cylinders. So there's a spec sheet on each one of the primary components. So here you can see the size of the tank. This particular tank, I think, is 900 diameter and 2.2 meters tall, and we need 2 of them. So very quickly you can get a feel for how big the plant room needs to be. There's our Habanero, which is our plate heat exchanger system for converting the mechanical water to the potable water. We have our 50 ml limiting valve, temperature limiting. We have UV on the return, and then the water metering system. This particular system was wired M-bus, so they've got on-site reading connected via the M-bus system. We have a partnership with a company called Choice Energy. They specialize in commercial solar. We don't do the solar system ourselves. We drive the specification for the solar system. So if the client has got an existing relationship with a solar provider, that's no problem. We just give them the shape of the solar system, the size of the inverter, the number of panels, which it needs to be, and then that goes out to tender as a separate contract. To combine the 2 systems together is very simple. There's a contact on the inverter, which we integrate into our controls, but it's not very hard. So Fronius is the inverter which our partner uses in solar. They're kind of industry standard in commercial solar PV systems. They've got a very wide range of inverters going from 3 kilowatts up to 15 kilowatts, 3-phase, and they run them in arrays. And then they use REC panels. Okay, so that is the presentation. I'll just bring this back up. So if there's any questions, I can jump back to the
Thanks, Darren.
slide.
That was very informative. Thank you so much. We are at the end of the session, but I think, Joe, if there's a couple of audience questions, or we can answer those.
Sure. So there's just one question from the audience, and I don't know whether you can speak to this one. It's more to do with a domestic situation. For a domestic home, integrating solar PV to a heat pump system, does one need a large battery to maximize savings?
In a residential system, typically, yes. You don't get that same capital efficiency that you do with a centralized system, so it doesn't fit together quite as well. One of the issues you've got with solar PV for residential is your usage is out of phase. So your peak power requirements at nighttime when the sun's not shining. So one of the advantages of this multi-unit accommodation, and also for business, is we can phase our system so that we use that hot water when the sun is shining. And that's why it fits so well together when you've got these two peak periods of, I use a lot of water in the morning, I can recover it during the middle of the day when the sun's shining, and then I've got a smaller peak period in the evening, which I can coast through. So that's why the capital efficiency of putting together these two systems works so well in this application, and it doesn't scale down so well. Once you get down below about 20 apartments, the capital efficiency really falls apart. And when you get down to the residential level, because your usage tends to be out of phase, it doesn't fit together as well.
Awesome.
Thank you. Do we have time for any more questions, or are we kind of on the...
We have come to the end, but I think if there are any more questions, if you can touch base with Waterware through their ArchiPro profile, or you can contact us directly. You'll also be sent an email after this with a link to rewatch this webinar. And also there is a post webinar survey if you don't mind filling that out. But thank you so much to everyone for joining us today, and we look forward to seeing you at the next webinar. Thank you again, Darren, and thanks, Joe.
Thanks, Holly and Joe.
Thanks, guys.